Welcome to my channel Physics for Engineers. I am Dr. Thirumalrao Gurugubelli, Associate Professor and Head, Department of Basic Sciences, School of Sciences and Humanities, SR University, Warangal, Telangana, India. It is the continuation to the previous video, the Advanced Scanning Electron Microscopy. We already discussed about the importance of SEM and the major components. We also discussed about the foundation of scanning electron microscope, that is the electron matter interaction. We also discussed the instrumentation and working principle of SEM. We discussed the major components of the SEM instrument in detail in the previous video. We also discussed about the secondary electron imaging mode. Here we discussed the importance of the secondary electrons in image processing technique. So now we are going to discuss the continuation to the scanning electron microscopy, that is the backscattered electrons and the sample preparation. Now let us discuss about the backscattered electron imaging mode. Unlike secondary electron imaging mode, which primarily reveals the surface morphology, backscattered electron imaging mode provides valuable information about the material composition. Backscattered electrons are generated through the elastic scattering mode. When high energy incident on the sample surface, the electrons interact with the atomic nuclei within the specimen. Some electrons are reflected back and leaves the sample surface. These reflected electrons are known as backscattered electrons. The key concept behind the backscattered electron imaging is its dependence on atomic number. Materials containing heavier elements scatters electrons more effectively than the materials containing lighter elements. As shown in the graph, you can see the backscattered electron intensity increases with atomic number. Therefore, the regions containing heavier elements appears brighter, while the regions containing lighter elements appears dark in the SEM image. For example, if a sample contains both aluminum and gold, the gold-rich regions will appear much brighter because the gold has a much higher atomic number than aluminum. This property makes the backscattered electron imaging extremely useful for composition contrast analysis. The working process begins when the electron beam scans across the specimen. Backscattered electrons generated within the sample are collected by the dedicated backscattered electron detectors. The detector measures the intensity of these electrons and produces an image based on the compositional difference. One important distinction between the secondary electrons and backscattered electrons imaging is the depth of information. Since the backscattered electrons originated from the deeper region within the sample, the backscattered electrons provides the information about bulk composition rather than just surface features. Here we have several examples where brightness increases with increasing atomic number. This clearly demonstrates how backscattered imaging can distinguish different phases in multi-phase materials. That we can clearly identify with the same image based on the brightness and the darkness of different regions of the same image. We can identify the different chemicals. The composition of the material can be analyzed using the SEM image by this backscattered electron imaging. The backscattered electron imaging mode has numerous applications in materials characterization. It is widely used for phase identification, mineral analysis, alloy characterization, inclusion detections, and failure analysis also can be done. The researchers frequently employed the backscattered electron mode to identify the compositional heterogeneity in the composite and nanostructured materials. Several operating parameters influencing the backscattered electron images and its quality. Higher accelerating voltage increases the penetration depth and enhances the compositional contrast. Working distance affects the detector efficiency, while simple tilt can modify the signal intensity. As important advantage of backscattered electron imaging is its ability to differentiate materials that may appear similar to the secondary electron images. For example, two particles within identical shapes may have completely different chemical composition. While secondary electron imaging would show similar morphology, but the backscattered electron imaging would immediately reveals the compositional difference through the brightness variations. In nanomaterials research, backscattered electron imaging is often used alongside EDS analysis. The backscattered electron imaging helps to identify the regions of interest, while EDS confirms the elements present in the composition of those particular regions. In summary, we can say the backscattered electron imaging provides the compositional contrast based on the atomic number differences. making it an essential tool for phase analysis, compositional mapping, and microstructural characterization. Now that we understand the major SEM imaging mode, let us examine the factors that determines the image quality in the SEM. We will discuss three critical concepts that determines the quality of SEM image. One is resolution, second one magnification, and the imaging parameters. Let us begin with resolution. Resolution refers to the ability of a microscope to distinguish two closely spaced features as separated objects. In simple terms, it determines the smallest detail that can be observed in the image. A high resolution image reveals fine structural details, whereas a low resolution image may blur important features together. Several factors affect the SEM image resolution. The first is electron beam diameter. A small beam diameter produces better resolution. That's why we'll use the lenses in the SEM to make a narrow beam diameter. The second one is the accelerating voltage also influences the resolution because it affects the beam penetration and interaction volume. Working distance plays a significant role as well. With shorter distance, generally produces better image quality. So it indicates that conventional SEM systems typically achieves a resolution of a few nanometers, whereas FESM instrument can achieve sub-nanometer resolution, allowing visualization of extremely fine nanoscale features. Now, let us discuss the magnification. The magnification refers to how much large the image appears compared to the actual object size. Unlike optical microscope, the scanning electron microscope magnification is achieved electronically by adjusting the scan area rather than changing the objective lens. SEM instruments can provide magnification ranging from a few times to several hundred thousands times. The advanced FESM system can exceed 1 million times of magnification. However, it is important to remember that the magnification alone does not guarantee image quality. Increasing magnification without sufficient resolution simply enlarge a blurry image. Therefore, resolution and magnification must always be considered together. Next, let us discuss the key imaging parameters that the first parameter is accelerating voltage. The higher voltage increases penetration depth and signal generation but reduces the surface sensitivity. The lower voltage provides better surface information and are often preferred for nanomaterials. The second parameter is working distance, which is the distance between the sample surface and the objective length. The short working distance generally improves the resolution and detector efficiency. The third parameter is probe current or the beam current. The higher current increases signal intensity and improves the image brightness, but may cause the beam damage in sensitive samples. Another important parameter is the aperture size. Smaller aperture improves the resolution but reduces the signal intensity. Whereas large aperture increases the signal strength at the expense of resolution. Scan speed also crucial in scanning electron microscope image processing. Slow scanning improves the image quality and reduces noise, while rapid scanning enables faster imaging acquisition but may produce grainy images. So the resolution is very less. We can also highlight the trade-off involved in SEM imaging. For example, increasing beam current improves brightness but may damage the delicate sample. Similarly, increasing accelerating voltage enhances the signal generation but may reduce the surface sensitivity. To obtain high quality SEM images, researchers must carefully balance all these parameters according to the nature of the sample and the information required. Beyond imaging, we discuss one of the most powerful analytical capabilities integrated with SEM is energy dispersive X-ray spectroscopy, commonly known as EDS or EDAX. While SEM images reveals the morphology and microstructures of the materials, the researchers often need to know an equally important aspect: what elements are present in the sample. This is where EDS becomes extremely useful. The principle of EDS is based on generation of characteristic X-rays When the high energy electron beam strikes the sample specimen, it can eject an electron from an inner cell of the atom. This creates a vacancy in the cell. To restore the stability, an electron from the high energy cell moves down to fill the vacancy. During this transition, the excess energy is released in the form of an X-ray photon. Each element processes unique electronic energy. Therefore, the energy of emitted X-ray is unique for each element and acts like a elemental fingerprint. The EDS detector measures the energy of these X-rays and generates an energy spectrum. The spectrum consists of peaks corresponding to different elements present in the sample. For example, if a sample contains titanium, oxygen, and carbon, the characteristic peaks corresponding to these three elements will appear at specific energies by analyzing these peaks. The researchers can identify the elemental composition. One of the major advantages of EDS is that it provides the rapid elemental analysis without extensive sample preparation. Within a few minutes, the researchers can determine which elements are present and estimate their relative concentrations, like atomic percent and weight percent of the each element present in the sample can be estimated using this EDS analysis. The EDS offers several analytical modes. The point analysis used to determine the elemental composition at specific locations. The line scanning analysis used to study the elemental distribution along the selected line. The elemental mapping used to visualize the spatial distribution of elements across the entire area. Elemental mapping is particularly useful in nanocomposites and heterostructures. For example, if we synthesize a Gc3N4 and Bi2WO6 composite, the elemental mapping can confirm whether carbon, nitrogen, bismuth, tungstate, and oxygen are uniformly distributed or not. However, the EDS has some limitations. Light elements such as hydrogen, helium cannot be detected effectively. The quantitative analysis may also be influenced by surface roughness, sample geometry, and detector efficiency. In nanomaterials research, EDS is routinely used to verify doping, confirms the composite formation, detects impurities, and evaluates elemental homogeneity. Therefore, EDS complements the SEM imaging by answering a fundamental questions, not only what the material looks like, but also what it is made up of. That we can understand from the EDS analysis. Now, let us discuss about the extremely important aspect of SEM analysis, that is sample preparation. Even the most advanced SEM instrument cannot produce high quality images if the sample preparation is not properly done. Poor sample preparation can result in charging, contamination, and image distortion, and also inaccurate analytical results. The primary objective of sample preparation is to ensure that the specimen remains stable under the electron beam and generates the available signals. Different type of samples requires different preparation procedure. For powder samples, a small amount of material is typically dispersed on the conductive carbon tape attached to the aluminum slab. Excess particles are removed to avoid agglomerations. For thin films, the sample is mounted directly onto the specimen holder. We must take care of the sample to avoid scratches and contaminations. For bulk materials, polishing may be required to obtain a smooth surface for imaging and compositional analysis. For biological samples, the additional preparation such as fixation, dehydration, and coating is essentially necessary because biological samples contains moisture and are highly beam sensitive. So one of the most important challenge in SEM imaging is non-conductive materials. When a non-conductive sample is exposed to the electron beam, electrons accumulates on the surface and causing charging effect. These charging effects may appear as image drift, brightness fluctuation, streaks, or complete image distortion. To overcome this problem, samples are often coated with a thin conductive layer such as gold, platinum, palladium, or carbon. The coating thickness is usually only a few nanometers and does not significantly affect the morphology of the sample. Another important aspect is cleanness. Dust particles, oils from fingerprints, and environmental contaminants can significantly affect the image quality. Therefore, samples should always be handled carefully using gloves, and clean tools. Proper mountaining is also essential. The sample must be firmly attached to the substrate to prevent. The movement during the process may result improper imaging. That's why to prevent the movement during the imaging process, we need to take care of the fixation of the substrate or the sample holder. In nanomaterials research, actual sample preparation is crucial because nanoscale features can easily be obscured by the contaminants or charging effects. Thus, sample preparation serves as the foundation for obtaining reliable SEM images and meaningful analytical results. Thank you for your attention. In the next video, we will discuss the important applications of the SEM. We will continue to explore more advanced characterization techniques and their applications in future videos. For more videos on the advanced characterization techniques, please do like, comment, and subscribe for my channel. Thank you once again. Thank you very much.